Ah, sorry. Yes, I guess I'm live. Uh, so much to keep track of. It should be acknowledged shortly. Thank you. I guess I'm live. Yeah. Okay, then. So I think we've done all the preliminaries necessary. And this appears to be almost the right size, but I guess I have to make it a little smaller. Or I could make the chat smaller. That's probably the way to go. Chat is, generally speaking, not of a high enough quality to be concerned with. So, yes, you can sort of read that. Charge, electricity, and magnetism will be the subjects to start with anyway. So, it's always been a problem for me in the sense that you have these things that seem so similar: charge, electricity, magnetism. And like this static idea, and you get a charge on you from the carpet and the spark on the doorknob. So here's a connection between this charge thing, whatever it is, and then this little electrical spark thing, and and then the association between electricity and magnetism is just so obvious. Yet there doesn't seem to be much of a relationship between magnetism and charge, except when it comes to stuff sticking to you. Just a lot of there's a lot of stuff that includes charge, electricity, and magnetism in terms of not only everyday life, like cellophane sticking to some surfaces, and even paper, and all the stuff we see in our lives. It's all over the place in a sense, and yet it's hard to connect the three words as being manifestations of something the same, because the properties, the thing that would connect all three of them, don't seem to behave in the right manner to be connected, like the electron, for example. So, like I pointed out, electrons being something collecting on surfaces, you'd almost argue that a magnet should be able to just collect electrons right off the surface. Yet it behaves just like any other charge element. It doesn't affect charge, in some special way. And you would just think that magnets would get covered with electrons on one end somehow, logically. So it just doesn't. Some of it just doesn't make any sense. It's hard to connect the three things as stated. And then, high voltages, low amperages, all of that kind of stuff makes it even more complicated. So I'm just saying that maybe that's a common thing. Maybe other people who have some experience with physics have also been troubled by the fact that they really seem like the same thing, but yet there's these huge disconnects where they don't connect at all. And that's always seemed difficult to understand. So I guess my point is that I think part of the difficulty in understanding was that you have these ideas about how things work, and if those ideas are wrong, that's why it can't work. So one of the wrong ideas is the whole, I think, understanding atoms as swirling things, I don't think helps. But the idea of a free electron, or electrons moving somewhere. And I think that was probably a wrong notion. So one of the first statements I'm making here is that there are no free electrons. The electrons have to be, you have to create an ion somewhere. You have to rip one off of an atom to actually move it somewhere. And that they don't move easily. It's the extraction is a violent process. So there's no free movement of electrons. It's and by movement I mean actually going from one place to another. They move, but they don't move somewhere. They do this. And so continuing the sentence, electrons just pass pressure in the form of bits, force bits. So the real the thing that matters about electrons is how they're what they're carrying in terms of connectedness to other material bits, protons and electrons. And that sort of defines the character of the electron, is what kind of arrangement it's stuck in. I don't know if it's the best way to say it, but it'll have to do. All right, let's see if there's anything else I have to say on the free part. There are things that, there's just all these facts. So I'm just saying that when I think about some of the facts, it makes sense. Because you think about charge in a vacuum, and the fact is there appears to be no free electrons for which you can move across a gap. You have to actually tear the electrons off of something and degrade it, cathode, anode thing. So you're not getting them for free. You're extracting them from something in a process that leaves the thing you extracted them from diminished, atomically damaged. But then you have the opposite argument where, like, say, a battery gets heavier as you pump energy into it. But, so that indicates it somehow is gaining matter, because you don't gain weight by collecting force. Force doesn't make you heavier. But clearly there could be an association. It could be another reason for that slight increase in weight, and it's really slight. It may not be proportional to the amount of energy, so you could logically say that it might have something more to do with the slight inefficiency that might exist of when gravity is essentially converted from gravitational pressure to pressure between the atoms and the bits inside of the atom. So the compression pressure that is inside the Earth, that's a reflection of gravity, is essentially although it's the same force, technically, it's moving through a different mechanism. So there could be an inefficiency in that conversion that would account for the fact that if atoms are more pressurized, they would weigh more, because their volume would take up more space. And taking up more space would mean that you're more exposed to gravity, and therefore you weigh more. Just saying, there could be explanations for that don't include actually gaining more mass, that is, matter bits, electrons or protons. All right. Electrons just pass pressure. Yes, okay, did that. Okay. So you could just go through all these different experiments, and they all show slightly different things. And so that's part of the dilemma of solving these. Not that it's a duality problem, but it's just a question that's open, in my opinion. Do electrons actually go anywhere freely? Or do you have to actually push them with a huge voltage to actually move one? And I'm arguing that, yes, you have to push them with pressure, and you're not pushing a free electron. You're pushing an electron that was somewhere, and now it's not there anymore. It wasn't free. Anyway, okay, so probably enough beating the dead horse. But it's sort of an important understanding, because once you understand that electrons aren't collecting on surfaces, then you can understand how charge, that electricity is just a manifestation of charge moving, the force, the pressure, going somewhere else, being exchanged through atoms. And understand what a conductor is and what an insulator is and why they're different. All right, so that would be the first thing to be clear on. So I begin the drawing process. So charge is pressure. So in an atom, there's there's a there's force reflecting between electrons, and then all the electrons are attracted to the positive center through the mechanism I've detailed in other videos, so I won't go into that. And they're repelling each other, and the reason why they can't move in is because of the pressure between them. So if I try to move this electron closer to the proton, it means that it gets closer. So if I move it in, it means it gets closer to these other electrons, and that creates more pressure resistance. So as you bring two electrons closer, you create more pressure because there's more reflections. The rate of reflection increases with distance. So the closer they are, the more reflections, which means the more energy, the expression of energy. And so therefore, the electron can't get through that barrier unless enough force hits it to push it through the resistance of those other electrons. And that's what's seen in a lot of experiments, that you need a certain threshold amount of energy to break atoms, or break through the exterior of atoms, you could say. All right, so the pressure of these, you could always argue it's probably the outside electrons, but theoretically, if I added more electrons, well, they'd be in a pattern like this, not like that, because they're repelling each other. If I added other electrons, you can sort of understand that these electrons would be communicating with these electrons, and these electrons would be communicating, so that pressure would be spread throughout the atom. So I'm not saying that as an absolute fact. I'm just saying it's likely. So anyway, so the argument, so the argument is that if you could have two atoms, and what really is going to change the atom is either you force more stuff. So if you thought of it as ping pong paddles with ping pong balls bouncing back and forth, you either add more ping pong balls or you bring the paddles closer together. So the idea would be that an atom of high negative voltage, I guess it would have to be, the difference would be they're closer together or further apart. So you could understand that the pressure could be either in the distance between the electrons, or again in how much force you have in between individual electrons. But the idea is that pressure would always balance between them. Small electron, high pressure, big small version of the atom. It would be high pressure. That means high electron pressure, and big atom is low electron pressure, which would be high negative voltage. Anyway, the difference between plus and negative would be the amount of pressure, and that all that's happening is a transfer between atoms of that pressure, and its migration through all the atoms that connect to each other, and eventually transfer that pressure. So the pressure is the voltage, and so it's sort of, you could argue that's the potential to cause change in a way. I don't know how else to describe it. It's just clearly there's high pressure and low pressure for the electrons, and yeah. All right, so that's one thing you can change in the atom. Now the trick is, so that's charge, that's voltage, and electricity is merely these atoms, these separate atoms, connecting, hitting each other, and passing the pressure. So this one hits this, it gets in contact with this electron. This one, say, is vibrating kind of fast. This one's vibrating kind of slow. And essentially the vibration, which is an expression of the pressure, is transferred to the other electron. And so it compresses this other electron, and it pressurizes the other electron. It tightens its structure, compresses it, or it in some it. Okay, so let's see how to explain that. Yeah, I'm just saying if there's extra force in here, it just spills the force into the other atom through these contact. So when the two electrons are forced close to each other, the amount of pressure they're both feeling will essentially be transferred to the two objects that are most directly connected to them, and they'll absorb any of this extra pressure. You could argue, like, say, if they got out of alignment a little bit, then pressure could escape, but the thing that would catch the extra pressure would be out here and out here. So the extra pressure can be transferred to the connected electrons. Something like that. All right. So far, mediocre. But it should get better. It should. All right, that's interesting. This will not go back on top of that. All right, it's good to know. All right, charge is not an amount of electrons. Okay, so it's the pressure between the electrons. And electricity is not the movement of electrons from one atom to another or a place to another. So the electrons, when a current's moving, the ping pong paddles that are the electrons aren't what's moving. What's moving are the ping pong balls. Okay, the pressure of the ping pong balls. So it just pushes, the electrons push the pressure along. So if I used this domino example yesterday, it's not terrible, but it's, say if you had a dominoes and they had little beads in between the dominoes. And when the dominoes fell, the beads jumped into the next space. And then those beads jumped into the next space. And those beads jumped into the next space. So the beads are moving, not the electrons. The electrons are just resetting, falling, resetting, falling, resetting. So they're not going anywhere. They're just transferring the beads, which are the pressure. Charged objects have pressurized or depressurized atoms. So I already did that. Not more or less electrons. So it's not about the number of electrons that decide whether you have charge or an absence of charge. It's about, well, if you have a positive or a negative charge, it's about the pressure. How much pressure is in the atoms themselves. The atoms have been pressurized. Okay. Electricity is the transfer. So you sort of can understand that there's some things they'll pressurize, some substances, and substances don't pressurize. So insulators would be hard to pressurize because the atoms don't connect in such a way that they can exchange through that domino movement those beads. They can't exchange the pressure easily. And so they only exchange the pressure on the surface. And they can't do it, they can't transmit it through the substance. And then there's things that would be very good at being charged, metals and conductors, because the atoms are very connected and they can transfer pressure very easily. All right. Electricity is the transfer of charge pressure. So electricity isn't really a thing. It's just the movement of things. So the real stuff. So the voltage, the pressure, is really the electricity. And you're just moving it. You're just moving the pressure. So when the pressure is moving, we call it electricity. When the pressure is not moving, we still sort of call it something, right? When your battery's charged, we call it charged. I mean, we don't call it electricity, but we know it makes electricity if we let it move. We let the pressure be transferred through a conductor. We know that's what it'll do. It'll move. So electricity is just really a way of saying, of acknowledging when pressure is being transferred. So when one thing is transferring its pressure to another thing, that's electricity. But that's really the only role something called electricity plays. The rest of it is just charge and magnetism. And we're getting there soon. All right. So once you understand that, that's a big simplification. There's just charge and magnetism. And unplug my vape. I have to use this one. Or I could use this one. I think that's a complete enough answer. Let's see, FOs, whatever, ology. What's the point of using the idea of fields to preserve locality? So I don't know who you're talking to. I mean, obviously they use fields for everything. So you're not asking me, right? Because I don't bother with fields. So I don't know the context of your question. Clearly they have to have fields because they believe in ether. You know, I mean, I don't know how else to put it. I mean, obviously everything is, they really do think everything's not a something. They think everything's a disturbance in a something, right? So, you know, that's all I can say. Well, locality is such a crazy word, right? Because the only reason why you'd have any doubts about locality is if you somehow believed in ESP or you believed in something magical. Because even in current field theory, the field requires this luminal speed limit. So, you know, I mean, when they say non-locality, they're basically saying outside the realm of light speed. Locality as in something directly affecting something else. Well, I mean, I don't even know. This direct thing just doesn't happen. As I've sort of pointed out, forces don't interact with forces, and matter bits really never hit each other. They just get close, and then the pressure gets really high when they get close. So two ping pong paddles, ball bouncing between them. I can't bring them a certain closeness. It's just way too much pressure. I can't create an external pressure to push the paddles together that can overcome the speed at the speed of light. So if I have a ping pong ball bat, you know, and it's moving the speed of light, if I bring those paddles a certain distance, you can sort of understand that the amount of impacts at the speed of light would be insane. And I can't create external hits at that volume. How do I do it? Besides bringing other paddles so damn, you know, that close. But beyond bringing two paddles out here into the paddles here and trying to push the paddles with more superluminal, I mean, with more speed of light impacts that are happening in like at an almost infinite rate, you know, I mean, so two material bits technically never hit each other either. So nothing directly interacts with anything. Everything's always a translation through matter communicates with matter with the force, and force communicates with force through the matter. That's probably a good sentence. That's one I should write down. That's why I'm making this video, by the way. I'm not doing it because I finalized everything. I'm doing it just to understand what more phrases I have to add to the, you know, what more details I have to add to this explanation. And I'm doing it because, like I said, this is really important, connecting these three things and understanding the difference between them. Like that one thing is doing one thing, voltage, pressurizing atoms. It's, you know, it's pushing electrons in or it's pushing electrons out, kind of a thing. That's voltage. All right. So yeah, I want to go on to the next thing. Need some more nicotine. But yes, the word locality is that's there must be a word for modern physics for some of their terminology that is of suspect origin, and the very idea of inventing some opposite to locality, like some idea that there's a locality and a non-locality, is just such a gimmick. Because it's almost like saying, if we had to call the universe the single universe, as if we were implying there was some other universe. So it's, the phrase, the words are jargony, just in the sense that they make implications for which there's no reason to provide reason for that implication. The best evolution theory, like there's something other than the evolution theory, not the best one. It's just a bad play on words. All right, so electrons and protons. So this is the other key thing. So besides there's no free electrons, I wish there was a way to bold things here. I guess I should just make it bigger. Let's do it. So we know this is the important one. And this one is huge. Come on, selection, please. That might help a little. So electrons and protons are the monopoles of magnetism. So they make it possible to create these objects that have charge difference, essentially. So they're electron heavy on one end, proton heavy on the other end. Electron pressure on one end, proton pressure on the other end, however you want to look at it. But that they're polarized. And so the pressure is the voltage. And to understand what the magnetism is, I sort of gave an example yesterday, but it's only atoms. See, a lot of metal atoms are structurally seem to be. It's like carbon. Carbon can be manifest in different forms, and one of them is graphite. And graphite, it would appear by all observation, is the molecules are really flat. And you can just lay them on. The atoms themselves are probably flat, and so they're just little. They like to go geometrically in one direction more than they go geometric in the other. So the atoms are obviously not some sort of perfectly round ball, because a perfectly round ball wouldn't do that, wouldn't collect in planes like that. So the metals are probably all atoms that are planar, okay? And by being on a plane, you can sort of understand that they could get lopsided. So if I have a round atom, perfectly round, like a baseball with a little center, it's really hard to move the proton to one end of it or the other end of it, because it doesn't break open easy. It doesn't change its shape. It's just not going to complement that. But if the atom in its structure has a ring, like a Saturn's rings of electrons, then you can sort of understand that if the Saturn lifted up or lifted down and left the ring behind, you could sort of understand that, yeah, there'd be a lot of ring on this side and a lot of Saturn on the bottom. And so that's sort of what I think the atoms that make up conductive materials that are paramagnetic must have a shape like that. So, this okay, so an atom that had this shape would be understood that if you turned it so you saw it on its side, it's, I've sort of twisted it this way, so then when you could understand that all the electrons are lining up. So, they just, I put it on its side so it's looking at you, this, coming out at you, you could understand that I could move the proton over here or over here, and this atom becomes very lopsided in terms of a lot of proton on one side, a lot of electron on the other side. And so the atoms that become magnetic are atoms that can do that they can polarize. They can stick out their electrons or stick out the proton. So the electrons can be pushed in relative to the protons. So you have protons and electrons. So if you had a surface, the protons would be here and electrons would be arbitrarily in places here, and that would be its natural state. And so when you bring the north end of a magnet or whatever, the electrons essentially are just going to move backward because they're going to run away, so to speak. They're going to move in, and the protons are going to be attracted, so they're going to move out. They're going to tend to. So those atoms would tend to twist to meet the magnet. And when they're going to do that twisting, they're all going to end up doing it the same way because the force is hitting them all very similarly. So whatever shape they take to meet the circumstance, that shape is going to be the same for all of them. That means they're all going to be lining up in a direction. And when they do that, they essentially become a magnet. That is, they start to filter any force that goes into them. It tends to migrate all the electron force one way and all the proton force the other way in terms of how it leaves the magnet. So it filters the gravity force and creates the phenomenon of this magnetic force, which is really just gravity segregated. So the difference between magnetism and charge is that charge is the pressure between the electrons, and magnetism is the shape of the atoms. And electricity changes the shape of the atom. So if you push electricity through atoms, what you're doing is essentially the same thing as bringing a magnet in, is that when the electricity goes through it, the electrons, to move the electricity, the dominoes essentially start to line up so they can pass the electricity. And by doing that, by pushing the electrons all in one way, again, you're tilting them. By doing that, you're arranging them. So you're taking things that were in different shapes, and by hitting them with force, they'll tend to bend all in the same direction because of the pressure. So pressure can cause a change in the shape of the atoms, and the shape change creates magnetism. Magnets can change the shape of the atoms. When it changes the shape of the atoms, that can cause electricity. That means that can cause, because you're pressurizing. So when you push the electrons in, you're essentially causing pressure changes. Those pressure changes are transferred, which means they're conducted, and it creates more pressure. So if I bring the north side of the magnet in, I pressurize the electrons. That is, I force the electrons closer to each other. So the material so you have to draw more electrons essentially to show this, but so you have more than one atom, in the material. So you kind of have to understand when these atoms are connected. When I pushed on these electrons and pushed them in, to the material, that means these are all getting more and more compressed. And the compression of these is essentially voltage. And that voltage, that extra pressure, has to move, will move. And so that's the electricity, that's the eddy current created. Is just that you're making extra pressure. When you push a magnet into atoms, you have to compress you're either compressing the electrons or expanding the electrons. So if you do the opposite end of the magnet and the electrons move out, then you're taking these electrons now are further away from the electrons they were connected to. So they went from, say, here to now out here. So they've created low pressure, but the ones here are still the same high pressure. So that high pressure will move from this to this one, and then from this to this one. And so it'll just do the same thing in reverse. It'll just transfer the pressure. So the pressure is what's moving from atom to atom, from set of electrons to set of electrons. And ultimately, it's the atoms that are individually charged. That's why charge can be on the surface of an insulator, because the surface atoms are charged. They're high voltage atoms. You know, you expose them, you can make them very high voltage. But there's very little density of that pressure. It's only on the surface atoms. Those are the only ones that are pressurized, because it doesn't convey the pressure to the other atoms. So the only ones pressurized are the surface atoms. And so when you bring an external surface that has low pressure, that low pressure will go zooming into that, the high pressure will go zooming into the low pressure ground or whatever, the less pressure ground. I have to learn how to say less and more pressure, because there is no pressure. It's always more or less. And so it'll just go zooming in, but it has no depth. So it has no amperage. It has no volume. Okay, so it could have a very high voltage, very high pressure, but very little amperage. So by the time it goes into my body just a little bit, it's already decreasing in voltage as it goes through me. So by the time it gets to the ground, it's probably 1 millivolt or something. So it could have started off as 200,000 volts at my finger, but by the time it goes through, it's such a weak amount of pressure. You just every atom is having it. Let's say it's diminishing very quickly as having any. It's weakening very fast. It's getting diluted in my. Get what ready for who? Cowboy, you're not a talking head. I didn't offer $5,000 to an asshole. So what does that even mean? Get the $5,000 ready, bot. Did you figure out how to get Michio Kaku or Degrassi Tyson or Walter Lewin, or you got a real physicist willing to do the job? You don't pay any attention at all, do you? You really don't pay any attention at all. Oh, amazing. Dumbass. So I'll delete that anyway. Worthy of deletion is nonsense, rubbish, meaningless, irrelevant. Just can't mean anything. Just can't. All right, so back to the story. So, so I think I've made that understood. So the connections are magnets move the electrons. When electrons move, they can create pressure, or they can create high or low pressure depending on which way they move. High and low pressure in a conductor can be transferred from atom to atom and moved from one location to another. And diluted, essentially, through that process of being moved, i.e. the resistance. Yeah, sort of. Let's see, what else? And so, yeah, so it's a lot like heat. So if you think about how heat moves through things, there's things that are good insulators against heat and things that move heat very quickly. And it's essentially the same rule. So instead of talking about the energy between the atoms, you're basically just saying that the atoms have a pressure, and when they interact with each other, they exchange the pressure, like they were exchanging heat. But it's not the same thing. But the mechanism is similar. All right, magnets don't make force. They just filter the force of gravity. Obviously, I've demonstrated that in previous videos glaringly and completely and brilliantly. But it's really important to understand that magnets aren't making a field, a magnetic field. They're not creating a magnetic field. They're just changing the gravitational field into one that's decidedly plus and minus charged, essentially. Plus force, minus force. But it's exactly the same number of little bits. So understand, yeah, I might as well try to illustrate it a new way or something. So where a magnet is basically just taking, this red is almost dead. Red is almost dead. So you can also understand why when a magnet induces magnetism in a conductor, you can sort of understand why it's happening, right? I mean, that's why it creates the fields that they create. Let me see. You got to be careful when you're talking about conductors and all right, I'll save that for later. Let's just go back to the radiation part. Yeah. All right, so you have a magnet. And if this wasn't a magnet, you can sort of understand that gravity goes in one side, gravity comes out the other side, gravity goes in this side, gravity comes out the other side. So this field would just be a bunch of, you know, red and black, red and black, red and black around here. So, but it wouldn't be the magnetic field. So right around me, you know, there's a bunch of red and black force, you know, gravity. And it's moving. The only gravity that's significant is the stuff, you know, that's demonstrating its existence or showing an imbalance. Is the stuff going down, right? But there's still gravity force, you know, going both ways. So I'm just saying around a magnet, it would be just a mixture. I mean, around any other kind of piece of material, it would just be all randomized. But the magnet changes that so that when you put a magnet in, the gravity, this was just gravity, and it was the gravity that came through this way and came out that side of the magnet, you know, so it's mixed. So obviously it's still mixed some because the gravity that came from this way or this way is still mixed. So it's not perfectly segregated. But half the field, all right, half the amount of gravity on one side of me or the other side, if I'm magnetized, is going to be now coming out completely segregated. So it's all red on one side and all black on the other, brown on the other side. And so half the field around the magnet is now decidedly separate in terms of it's separated the two forces, and therefore the forces can have a dramatic effect on another magnet. So if I put another magnet there, it's going to detect these changes. If I put a glass of water, it's not going to detect it. Well, a glass of water is a little tricky because yeah, water can carry a charge, and when it carries the charge, it's magnetic. But you know, I don't want to get into that. It's not even when it carries a charge. When it's actually charging, it can produce a little bit of magnetism, and therefore you can move it with a magnet. But see, that's what I mean by there's just so many little experiments, and all the little ones have to be explained as well as the big ones. Right. So, what else do I want to say? Yeah, so I could argue, just since I have the drawing here, that when you bring a magnet in contact with, a piece of ferrous material, I'm going to draw it as blue. The electrons are going to be attracted to the red side, so they're going to move forward. So this side of the magnet now has protons here and has electrons on the inside. So protons on the outside, electrons on the inside. And it's essentially going to force this other thing to put its electrons on the outside because there's low pressure, the red force, and the protons are getting repelled, so they're going to move to the inside. So that's why a magnet creates an opposite magnet instead of the same magnet. It's just simple. If it's an electron outside, that means it's going to push electrons in, and then that means protons are going to be popped out. So it's always going to be an inverse relationship. So when a piece of ferrous material is caused to become magnetic, it's always an opposite magnet to the field that is causing its magnetism. So they talk about eddy currents and then resistance to change, but there's not really any resistance here. It's just complementary. It's just logical, the logical consequence of pressurizing and depressurizing fundamentally electrons. I mean, you could argue the whole thing just from the perspective of the electrons. The electrons would be attracted to the protons on the surface. So you can just use them to turn everything. So you don't really need to think about both forces. You can just think about the electrons. And the electrons probably are the major player in everything that happens. Which brings us to photons, which I don't know if I should include in this. So maybe I should say, because photons they're the stuff trapped inside this. They're the pressure, essentially, between the electrons. So it's probably a sentence I should throw in here. I just didn't want to get away from the idea of just doing the three subjects, but it's probably an important, charge, electricity, magnetism, ... and photons. Because photons are the charge, they're the pressure. They'll be created when you break the atom. They're the pressure between the electrons that will be released. So if you pull an electron off, you're going to release, some photons. And whatever the pressure of the atom was to cause that release, right? You put a lot of energy in to knock an electron free, you're going to create high energy photons just because you had to pressurize the atom to knock the electron free. Yeah. All right, so we've kind of done magnets don't make force, they just filter the force of gravity. So there's no there's no magnetic field. It's just gravity. I just have to come some converted. I mean, it's such a simple conversion, right? It's such a simple change. Just going, well, put the heads pennies over here, put the tail penny over here. I mean, it's such a simple change, but it's obviously a tiny change that makes all the difference. Huge difference. All right, so and finally, the neutron is not an elemental bit of matter. So just to make clear, they named the neutron 100 years ago. They made a mistake. It's not really a neutral player. It's not really an elemental particle. it's clearly composed of an electron and a proton, and it's a dipole. It is a dipole containing an electron and a proton, as stated there. So there's no, it really isn't, you can understand that, yes, it's necessary to keep the protons together. You have to have the neutrons to be able to get the protons close. But other than that, the neutron isn't a charged element. It's made of charged elements. And E equals P is the little bottom there. Just, you know, energy really is pressure, not mass. The electrons are nothing. They don't weigh anything unless they don't mean anything unless there's a force to hit them. And that's kind of it. You know, the force is the energy in the universe. How much of that energy has been collected in compressing things, moving them closer, moving them close together, and then locking them in that condition. And that's what is happening inside of the sun, is this complex arrangement of the atoms, you know, where there's the proton in the middle and the electrons. They're creating a stable magnetic arrangement. It's just really just you taking magnets and positioning them in just the right locations, you know, head north, south, where they can't move from those locations without being pushed by some other magnet. And it's kind of all theoretically possible, you can think, you know, if it wasn't for this, if you make a big model, you're going to jiggle it too much, you know, and it's going to break. So even if you got them all to do that, you know, any movement, and it's like a house of cards that falls apart. But obviously on the nuclear scale, that's not the same problem. These little bits get bigger and bigger and bigger. So if we could make giant magnets, we could clearly probably put them in space and get them to stay in exact positions pretty reliably. Yeah, pretty much. So what else do I want to say? Anything else? Yeah, so this wasn't as, I wanted this to be a little snappier. But again, it's more for my, to improve these bullet points even more. And again, just emphasize my realization that this is an important step in this theory, is being able to make this connection between charge and magnetism in what I think is a perfectly understandable way, that electricity magnetizes because it changes the shape of atoms, and when you compress atoms, you're going to cause extra pressure, or decompress. You're going to change their pressure. Changing their pressure means changing their voltage. So clearly a magnet is going to change the voltage in a conductor when it's compressing. And that voltage is only going to, that compression is only going to mean something as long as the magnet keeps moving, right? So if it stops compressing, it compressed and that's it, then nothing can happen, because the pressure just moves through the other atoms and that's it. It's the end of it. It doesn't go anywhere. So to keep pressurizing, you have to keep moving the magnet to make more voltage. They can always do this by putting an ammeter on a wire. Let's say you have a wire and then you move the magnet in and you get a little tiny reading. If you didn't put the ammeter there, the voltage would still be in the wire, you know, technically. So that indicates that the pressure moves in decidedly in directions. No, it wouldn't still be in the wire. You have to think about it. It would be diluted by the wire. So there wouldn't be any The entire wire, yeah, the wire gets hot. That's the obvious answer. It's converted into heat. So there is no, can't store it. And that's why you have to be careful, so careful, in what you say. Whatever the fuck that was. Because there's always something, some fact, that you have. Oops, I didn't consider that fact. So yes, so it can't. A conductor can't store because a tiny bit of extra pressure goes in, and it does actually spread through all the other atoms. So it increases the voltage of all the atoms a little tiny bit. So you need to make a lot of voltage before you're going to be able to store a voltage in a wire. You have to make a lot of pressure. And the problem with using a magnet is if you move the magnet in, then you move the magnet out. Now you're pulling pressure out too. So an alternating current, an alternating magnet going in and out, can't possibly can't make a sustained voltage. It makes a voltage that just, you keep going from low pressure to high pressure. So you just keep changing the direction of the electricity, the flow of the pressure. But you're not making the pressure bigger. But technically you could if you could just keep moving a magnet in one direction and you didn't have to move in the other. So if you moved it fast in one direction and slow out, and then fast in and slow out, you could probably build a charge up on the conductor. That is, the conductor would charge. And especially if you use just one side of the magnet, like the positive end of the magnet. I mean the north or the south pole. I think that would work. Hard to say. All right, I shouldn't have gone there. I mean, charging a wire is just something we don't need to talk about, but obviously you can do that. So that's the other thing. I mean, there's so many things to talk about charge, like how you can make it move from one thing to another thing, and how, it really is just about collecting pressure. So when they think they're collecting electrons, they're really just collecting the pressure. So if I charge a metal plate by say putting it on something I've put a charge on. So I have something I've put 10,000 volts on, and then I put a metal plate on top of that, and I touch it. I'll force the voltage into the plate. Okay. And then I can, just because now there's a ground, there's a low pressure. So I'm just adding a low pressure and creating the circumstance where now it'll be transferred. There's something to exchange. Where when it's all the same pressure, there's nothing to exchange. So you have to create a circumstance where it can be exchanged. There's some place to go. It has to be an open door somewhere. So it's like if you want to blow air into your house with a fan, you have to have some window open somewhere for the air to go, or it's not going to go. It's no current. It's going to happen. So there has to be a way for the pressure to go to low pressure. It has to be a low pressure door somewhere. Or you won't move the pressure. The pressure will just stay where it is. I don't know if I want to like this. Dark helmet. A movie character. You should totally, I just love that, hit up Cool Hard Logic with your offer. Why would I do that? Who's Cool Hard Logic? Yeah. Anyway, he has a degree and might be willing to invest the time to learn about your theory. You could do a World of Batshit special. Okay, well, I have to go find out who Cool Hard Logic is. But I'm not too confident, but we'll find out. And then maybe it'll be worthy of a subscription or something. Who knows? So let's go to some page I don't need. Yeah, this one we don't need. We can search in here. See who this guy is. Cool Hard Logic. So he has 97,000 subscribers. Not bad. pulling silly beliefs and nonsense to the test, putting for education and amusement. Thanks for watching. Okay. Doesn't sound so bad, but he obviously doesn't do the real person thing. So he's just doing the voiceover thing. Oh, anyway, let's go to the channel. I suppose I can subscribe for 10 minutes. Oh, yes, they're all cartoon videos. Wonderful. Yeah, I just don't think that's, I just don't think you can do serious things with cartoons. Things that are worth doing. But anyway, let's see. I'll subscribe for now. All right, let's see. Testing flat-tards. Why would, obviously flat Earth is retarded, so yeah, it's a waste of time to even. Why would somebody make 5 videos on that subject? Let's see. World of Batshit number 9, Wildfire. That doesn't sound too interesting. Number 8, North Pole. World of Batshit. So the North Pole is batshit. I don't know what that means. All right, more flat Earth stuff. Mirror, the living dinosaur returns. It doesn't sound too good. Oh, come on. I mean, all these stupid flat Earth videos. Yeah, so I mean, look, I mean, frankly, I'm not too impressed when somebody's kicking retarded people. I mean, that's just too easy. Anyway, let's see. Musings on Special Snowflake. That doesn't sound too good either. False copyright claim on World of Batshit 5. It's Fearless. Can we find, oh, here we go, gravity, good. Let's see what we got here. Thank you. So
when a certain demographic can't understand something, the conclusions they reach are off the chart. Welcome to World of Batshit.
Yes, whatever. Very educational.
Flight. First developed by insects of the Devonian some 400 million years ago, nature has solved the problem of gliding and flying several times since. However, its most sentient earthbound mates had to wait until they were spending more time thinking about how to take to the sky, instead of wasting their lives talking to it and pretending to get responses. In 1783, they joined the club, when the Montgolfier brothers made the first manned hot air balloon flight.
I'm a little surprised this has 372,000 views. A little surprised.
Sustained powered flight would have to wait another 120 years for the Wright brothers. In 2016, commercial aviation is expected to carry 3.6 billion passengers, for whom flight has become a commodity.
Whatever. I don't even know if it becomes a commodity. That almost sounds silly. I mean, I don't think anybody's, I mean, the people flying aren't making money flying. You know, they're making money getting to one place or another place. But, you know, that's not even a proper way to phrase it, I don't think. Flight, a commodity. Yeah, airlines go bankrupt all the time.
The principles of flight are now well understood. So imagine, if you will, dear viewer, my dismay at finding that there are people out there who think they can use it to show that gravity is just another conspiracy. Here's one. He's got a channel called BS Detector, which is ironic as he fails to detect the horrendous bovine stench emanating from the digital manure he uploads for the consumption of people.
Well, let's get to the details, please. All the ad hominem mocking bullshit is sort of unnecessary. Just get to the point that, hey, look how retarded this guy is. And why don't you just figure out whether he's retarded or a liar? Because that is a difference, right? There's people who lie on the internet, and then there's people who are really dumb.
Even dumber than he is. He's a flat earther who thinks satellite.
Oh, here we go. So that's it. This is this guy's theme. Flat Earth, flat Earth, flat Earth, flat Earth. I will go out and kick midgets and retards.
Don't exist. that the moon cannot reflect sunlight, that the equator is impossible, and that there is a dome above your head. He also trumps Bill O'Reilly's stupidity in not understanding how tides work, apparently working on the premise that if you can't understand the results of a Google image search, or that diagrams of physical phenomena are really drawn to scale, then there's a conspiracy. Like many conspiratants, his video output rate is prolific, which suggests a possible correlation between making it to adulthood thinking that Earth is flat and being unemployable. In this video...
So this is just like I said, what's the point of all this much? Okay, you could just point out how flat Earth is worse than religion. I mean, God theories are more plausible in the sense that they aren't direct contradictions of possibility, in the sense that the impossibility of a 5 million person conspiracy to cover up the fact that the world is flat would be just too ludicrous for words. It can't happen in any universe.
He haphazardly attempts to explain why there's something fishy about gravity by using the conspiracy stalwart of stumbling from one question-begging argument from ignorance to another. The quality of argumentation you're about to see from BS is so piss-poor you might wish to pause the video here so that you can evacuate your bowels and bladder, strap yourself to your seat, position the screen out of punching...
Yeah, it's okay. I could say the same thing to you here. This fucking kindergarten music in the background. You know, you're just using all these famous, funny things, you know, to shtick, you know, other people's failure. You're just playing a fail video, right? I mean, oh yeah, everybody just loves to watch fail videos. I mean, this is just kind of gratuitously bullshit. I mean, you know, science for imbeciles. You're just basically saying, oh, I'm talking to idiots that need me to point out that, hey, flat earthers have a real theory that we have to debunk. No, they don't.
Range and double up on the oven gloves. Ready?
I mean, all I have to do is point out that, look, the flat earther guy is saying these, like you listed them, these silly things. That we never landed on the moon, Walter Cronkite was a liar, everybody with their tons, billions and millions of liars, all these people working for McDonald's, they're all liars, they're all cheaters, they're all paid off by the government to lie, or they were all killed by the CIA and they never really exist anymore, or some kind of bullshit. And you just say, isn't that preposterous? I mean, really, none of them could figure out how to call the National Enquirer and say, they forced me to tell you there's a round Earth. And we're done now, right? We're done. This is too stupid to have a conversation about, right? I mean, I've seen the satellite images. It just, forget it. It's over. Non-starter. Too stupid.
Let's go.
Man, I was just cruising on this airplane, looking at the flat horizon that rose to my eye level, looking at the sun, which was...
All right, so he's putting hillbilly music behind it. You know, just all this is just all little gimmicky things. Yeah, obviously he doesn't sound too smart. Sounds like he's drunk or druggy. So, yeah, he's just playing with imbeciles. I'm going to jerk around some people. Just like, look, all the people in the past who said they saw UFOs were all liars. They just wanted some attention, right? The crop circle thing, it's all people seeking attention. This guy's just seeking attention by saying something so outrageously stupid that other people say, oh, let's go kick that retard. And he's loving it. He's saying, great, thanks for making me popular.
Really close and big.
BS doesn't go into any detail about how he established the distance to the sun whilst aboard this aircraft. In reality, he's utterly failed to take account of glare, which in itself tells you nothing about the size of the light source or the distance to it. So how does he know that the sun is big and close just by looking at it with his eyes? He doesn't, and he can't.
How long have we been traveling at this altitude? It seems like we haven't been changing our altitude at all.
BS apparently expects his altitude to change throughout the flight. You can probably see where this is going already, but first, let's summarize flight. Lift is one of the...
Oh, no, that's dangerous in itself. But anyway, lift is crap. It's all where you point the damn thing. Plane goes where you point it. It really is that simple. Wings they're little helpers, but they don't really have anything to do with anything. Plane goes where you point it.
Four forces acting on an aircraft. To maintain lift, a wing needs airflow. However, any solid object moving through a fluid such as air is subject to drag. On an aircraft, this is due to factors such as friction with the air and wingtip vortices, which is why modern aircraft have winglets to enable smooth airflow and improve fuel efficiency. BS is on just such an aircraft, and it appears to be an Airbus A320. Drag, as you'd expect, needs to be balanced with thrust to maintain.
Oh, forget it. I can't do this banjo shit. Amazing. All right, anyway, this is a way more complicated answer than is required to answer the question. The simple truth is, when you're looking at the sun through the atmosphere, you're not going to see it the way it is. Oh, Jesus Christ. Not even going to be the right color. All right, so he shows some satellite images. So all this, 20 minutes to make another argument to debunk a flat earther. And there really isn't anything about gravity here. Let's see, maybe here he's going into gravity.
And the camera is pointing in, or what the orientation of the ball is. Flat earthers like BS say there is no gravity acting on the ball. So in what direction will the ball fall? The air pressure is, to all intents and purposes, identical on all parts of the ball's surface. What will make it move? Why would it move in any one direction?
Right, so air pressure, see, he's drawn air pressure as straight lines, which is sort of a mistake, because air pressure isn't a straight line force. Air pressure goes straight line into little balls, and so the little balls spread the pressure all the way around. But air pressure doesn't work the same way as a straight line force.
Over any other. It's a testament to the breakneck speed of flat Earth research that despite having the same length of time to explain reality as the rest of humanity, the vermin who think gravity isn't a thing have yet to explain why a ball would accelerate in a particular direction in preference to any other. Another thing which BS's density explanation has failed to account for is something we noted earlier, that the density of Earth's atmosphere decreases with altitude. Or, to put it another way, the density and pressure increases the deeper you are in the atmosphere.
All right, so maybe I should do this to conventional physics, right? Just do a bunch of this graphics crap and then go, these wackos, they invent dark matter and then they place it wherever they want to and really have no theory. Then I can go on Magnetism and say, they have this thing, a virtual photon, this magical nothing thingy, virtual and shit. It's on the internet or something. It's not really there. And it somehow conveys to everything, hey, you have to move, you have to flip over, you have to do all these magical things. I told you so with the virtual photon. With the, I sent you an email. So I could mock it and make fun of it. Not incredibly productive.
Due to the weight of the air above, in just the same way as water pressure increases with depth. This property of the atmosphere is why air pressure can be used to determine altitude, and Joe Public can...
Yes, and the important thing to understand is gravity is causing every bit of that. Every bit of pressure is all being created by the one force. The one.
By altimeter watches that work on that basis. The relative concentrations of gases in the atmosphere remain essentially the same for tens of kilometers due to turbulence and mixing by winds. If density were responsible for the effect of gravity, the air shouldn't get thinner with altitude because it's all the same stuff and there's no gravity to pull it toward Earth, making the pressure higher.
Yes, the simple answer is gravity is a nuclear force. It's hitting the little bits. It just doesn't care about. It hits you with exactly a force proportional to your mass. So if you're heavy, you absorb lots of it. If you're light, you absorb a little bit of it. So it always affects you exactly as much as you weigh. The number of having the, if you don't have any electrons and no protons, no gravity. None. But you have electrons and protons, that hit the gravity will hit those. And that'll move you. So again, a much more complex answer than necessary.
Closer to sea level. And yet reality disagrees with the flat Earth.
So let's understand, their version of reality is that gravity thing is bent space-time. Whatever that is.
Conjecture that gravity is just density.
The constant vacuuming of space-time by every little subatomic particle is vacuuming space-time as hard as it can.
It gets worse though. If we follow the implications of BS's density conjecture, then the acceleration toward Earth of an object should increase as air is removed. What then should happen in a vacuum? Since flatards don't do predictions, we'll have to do their work for them. They have two possibilities.
Oh, I really hate this. Just don't know why people think that's. I mean, I guess again, like I said, apparently it's something idiots need. You know, is they have to have music put. They have to have the opus of a sentence or something. It has to come orchestrated with music. I just don't get it.
The first is that acceleration is a function of the ratio of the densities. In a vacuum, we have an immediate problem. You either divide by 0, suggesting an infinite acceleration, or the ratio is 0, in which case the object won't fall at all. These are both clearly horse shit. The other rule.
I don't know if that was clear at all, or whatever. Oh yeah, he wrote infinity divided by infinity equals in one infinity. Yeah. I don't think it really explained it to the idiots listening to the banjo music.
Alternative is the difference in depth.
It's funny, this keyboard really should work. I found a way to do it. It's just the right speed.
Is
I have to
relevant.
hold it. No, this doesn't work. Bitch.
In that case, as the surrounding medium's density tends towards 0, the object's acceleration should get faster. Well, this should be easy to test experimentally. Unfortunately for flatards, when you remove the air from a container and drop objects at very different densities, they not only fall at the same rate as each other, but they still accelerate at 9.81 meters per second squared.
Right. So, I mean, just there, you're done. That's all you had to do. Just show the experiment. Just say, look, here's the experiment demonstrating it. The feather is less gravity hitting it. The other thing, more gravity is hitting it because it's heavier. And so if they were moving sideways, you could sort of understand that. If I have to push a 10-ton weight or I have to push a 1-pound weight, I can understand I got to push one of them a lot harder. So yeah, that's true. But gravity does that automatically because gravity is affecting the atomic weight. It's affecting the matter bits, the electrons and the protons. Also the neutron, which is electrons and protons.
Flatards need a formula to calculate acceleration where no matter what densities you input, the answer always comes out as 9.81 meters per second squared.
Right, okay, so anyway, we got enough of this, right? So this channel, I hope he has something other than flat earthers. So I guess I'll have to see if he has an email address and see if I can, but I mean, it's too bad if it's all this bullshit. Spirit science and the galaxy of lies. So obviously religious science is really, that's another just, you know, you're picking on retards. I mean, I wonder if he does the electric universe. That would be a good one to take on. And certainly he ought to debunk the Pharaoh cell. You know, there's lots of people using that to invent all kinds of theories about magnetism. So, testing doomsday predictions? They really have to know something about physics to do that. And I don't think you people really do know. I think the doomsday, then you can't even figure out where the universe is coming or going. It's getting bigger, getting smaller, moving, you know. Anyway, let's see what the about page says. Thanks for watching. Details, best viewed resolution. Some videos have subtitles, captions, ink, links. Don't have any links. Don't have a website, apparently. So, I guess the only way you can contact him is to make a comment on his video. That's not too great. So Alan Key, BBC Earth, The Living Dinosaur, NASA Jet Propulsion. No draft physics on the recommended list. All right. Yeah, so we're kind of out of luck here. No links. Yeah, there's just no links. Well, he has a Google Plus, but I don't know if I want to go there. I don't like Google Plus much. So, yeah, so you're stuck making a comment on a video? That sucks. So if anybody knows how to contact this guy, let me know. And yeah, we'll see what his price is to debunk me. Try to humiliate me, you know, with banjo music. See if he's up to the task. I don't think he'll do it, but we'll see. He'll fail. If he tries, he will fail. That's my prediction. Tries, he will fail. Yes. So, yeah, let me say, 97,000 subscribers. Pretty good for pretty lowbrow content, too. Again, picking on children and shit. Yeah. Come on, take on take on somebody with a little more balls than, you know, these wackos. Somebody who can fight back. All right. So that was interesting. Thank you. Appreciate it. And such. So put the text back up. All right. We should totally get a petition going for this to happen. Well, I hope I don't have to do that to get it to happen. I think we should totally, I guess, go comment on his video saying you need to make fun of draft science. He'll kick your ass. Yeah, that's what we need to do. Why are you running from draft science? Why are you hiding? Yeah, I mean, I'd love to get one of these guys, you know, Thunderfoot, one of these arrogant, I'm so fucking smart. Love to get them on the hook. So I guess I should put my text back up just for the fun of it. Where is it? It's probably underneath this idiot. Call me an idiot. What's hate speech? Something like that. All right. So nothing else to add. So yeah, so I should probably add photons in here because it sort of is important. But they're really not charge, electricity, magnetism, photons. It really just isn't. But there is no electric field. There is no magnetic field. There's just gravity, and you can polarize it. So there's only one transmitting field of energy. The field of energy is always magnetic in the sense that it's always just segregated force. Electricity is atoms banging into atoms. Electricity isn't force moving through space. It's force being transferred from atom to atom to atom to atom to atom. They have to do it through the atoms. That's why it has such a hard time getting through the atmosphere and makes all of that light. It's because it's a brutal process when the conductor is very, very weak. and such. Yeah, I don't think I have to, you know, like I said, it's not exactly the video I was intended, but draft physics is the channel, and so I'm still in the draft. I'm still I have to rewrite this stuff to be really, you know, get right to it. So I'm figured in the process of attempting to explain it, I should be able to acquire some new phrases or analogies to make it understood what's happening. So the charge creates pressure. Magnetism creates shape. And electricity is merely the movement of the pressure, which in paramagnetic materials changes shape. So to move pressure, the atoms change shape in a conductor. And that essentially defines conductors. By changing the atom shape, you polarize the atoms and therefore create magnetism. So the electricity doesn't directly convert into magnetism. The electricity converts the atoms in the material. So this is something that needs to be put in there. The electricity converts the atoms in the material into dipoles. And that, those dipoles create the magnetism. So there's no direct connection between magnetism and electricity. There's the indirect connection of changing the shape of atoms, compressing the electrons, uncompressing them, pushing them to one side, you know, polarizing the atom in the process. When you move the electrons, you are going to tend to polarize the atom. You can't really move the electrons without polarizing the atom. Sort of a intrinsic consequence. Sorry, my monitor is misbehaving. Been really better lately. And I've only had to fix it once a week or so. So what else do we have here? Anything else to discuss? Yeah, it is really, I don't know exactly why YouTube got rid of the messaging system, but it really seems kind of, it was never very good. It was an irritatingly bad system. But, you know, I mean, you should be able to privately contact somebody. I mean, I shouldn't have to write you know, I shouldn't have to correspond to this guy in public. Yeah. I mean, I shouldn't have to say, well, how much would you charge me to debunk me, make a fool, to attempt to make a fool out of me? How much do I have to pay you to attempt to make a fool out of me? I have a big problem with the word classical mechanics. I think it's just such a lie. You know, there's truth and there's complete, you could argue, and there's incomplete. So if you want to say, well, you know, 200 years ago, they didn't have a complete theory. Oh, okay. But this idea of calling something classical mechanics versus what? Super modern fun mechanics? I'm just saying that most of the classical mechanics is dead correct, 100% correct. It just doesn't explain everything. It doesn't say anything about a lot of other things. It just says one little thing. And that one little thing is fucking right. I mean, when Newton observed the inverse square law, we haven't fixed the inverse square law, right? I mean, it still works, right? It's still the right answer, right? I mean, I could argue that there's lots of little waste bits that we can't account for in just the mechanism of me pushing something through friction. There's lots of our math that is made out of generalizations that doesn't really account for every single little bit of the energy transfer. So what is? Yeah, but what modern physics do I need when it comes to those simple things, like two rolling balls colliding with each other? I'm just saying that this calling it classical mechanics is just taking a cheap shot at the historical database, which isn't that flawed. It's a pretty good database. Who's going to decide who won the debate? Well, I don't care about that part. I didn't say I even want a debate, but I certainly would love for him to do a live room or something. That would be excellent. And I already said it would have to be a collection of people. So yes, a collection of viewers who aren't complete assholes. So I guess it would be maybe you, maybe FO sociology guy. You know, lots of people could be perfectly reasonable candidates to vote. But again, I don't have any. I'm not worried about your vote or anything like that. My point about having the vote was if a bunch of guys try to debunk me and we have a contest, you know, so I'm going to pay $500 to whoever does it best. Now that's a different kind of, like I said, I didn't say I'm going to do that. I'm just saying if I did the contest that way, instead of paying people individually, you know, maybe I'd get more people interested. So maybe that would get me more debunking videos. So the idea would be is they make a response video debunking me, and then you people would vote on who did the video that deserves the money. Now, I would hope you wouldn't give it to some asshole. Again, I'd have to have some veto right, because you're not going to give I'm not going to pay somebody to make a clown video. Okay, if all that guy's going to do is play banjo music and have, you know, confetti vomit fly out of a video of mine, you know, take a video of mine, have confetti vomit flying out of my mouth, I'm not paying him $500 for that. That's not debunking me. Okay, you don't get $500 to mock me. You get $500 to prove I'm wrong and stupid and ignorant, and that I've made a huge, colossal mistake. Why would you pay for that? The other guy's gonna insist he debunked you. Why would you pay for that? Like I said, I'm not going to pay for a crappy video. So that's the whole point I'm making. But it's going to be sort of your people's choices. I'm just saying I tend to believe that you people aren't going to vote for that kind of stupid video winning. I'll hopefully have a physics degree in a year. Well, that's close enough, frankly. You know, you want to try to prove me wrong, but yeah, you obviously don't think that you're not entirely confident that you have the physics to prove me wrong, right? I mean, even if you didn't want to prove me wrong, you'd have to concede that I'm not going to be easy to prove wrong, right? I mean, even with the knowledge you have now, you're a 3/4 physicist. You know, could you admit that, well, yeah, what you've put together, you know, ties up pretty tight? I mean, it doesn't have any like obvious boogers hanging out of it. So there's not something obvious that you can just laugh at and say, oh, that's ridiculous. You know, that's completely easy. I can just show you one experiment and just debunk everything you just said there. I can show a leaf and an apple falling in a vacuum tank, and I can, you know, demonstrate. No, you can't do that because it is a tight theory. It's a damn good alternative to the present mush, and it has the incredible advantage of being a unification theory. So, I mean, it's not only as tight as the current mush, at least that tight, it's a unification theory. It's totally wins for that reason alone. But yeah, it really, you know, really I'll have to see if I can get anybody interested. Like I said, if they would do it for $500 or do it for a $500 prize, or they would be willing to, you know, because there's you got to put some effort in. I mean, they do have to actually watch a couple of my videos and to get the idea of what I'm saying. Well, the website listed below is essentially the only documentation I've got that's complete in any way, but it's not entirely accurate either. So most of it is. So it's 90% correctish. But it it doesn't have all this new stuff I've been doing. So you go to draftphysics.com and you hit the more button, and you get the whole document. I have to put the whole document on the home page eventually. Well, the best video to watch, I think, is the one I feel really good about. Was that one I titled "The Most Important Physics Video Ever Made." 7 videos ago or so. I have to put that in the Start Here category. I mean, it's hard to say. The Start Here videos aren't bad either. So I don't know which ones are better, the overview videos or the Start Here videos. I guess I'll have to watch the Start Here videos and figure out whether they suck or not. It's just I don't remember. A lot of videos. But at least I have been titling, in the last 6 months or so. At least they all have better titles. So you can usually find any subject. You can find it by just typing the word lensing or gravity or electricity or something, and you'll get the video on that subject. So, Antelope Guy, have you done, if you're still there, have you done the part of physics where you go into all the refractions and stuff in lenses? Because, mirrors and lenses, man, that stuff gets really simple formulas, for refraction and transmission. But yeah, it gets pretty gnarly because that really relates to the interferometer in so many ways. I mean, the whole optics subject is really, I just wonder how, for a standard physics degree, I wonder if they force you to do all that optics shit, or whether that's just for optometrists or something. Yeah, so you already did the optics? There's lots of interesting things. I mean, it's like the coatings on lenses that eliminate the problem of reflections, and it's really kind of messy when you think about it in terms of the Newton context, because you're saying, okay, it's a thin film on the outside of the glass, but the glass, it must be transmitting the photons through the film layer to the glass layer. Because if it wasn't, it couldn't change the reflectivity of the first glass layer. The glass layer would still be reflective. So it kind of proves the point that if the two surfaces are in contact and there's no layer between them, that the light is transmitted and not reflected. The layer doesn't mean anything if the atoms are so close, there's no layer between them. So any layer, you can have layer differences. You can have many layers, but if you have the layers so close that they're in contact, actual physical contact, atom to atom, then there is no reflection. off the layers, and they never make that distinction. That it really is just about having gaps, slits. It's about gaps between things. And if you don't have a gap, you don't have any you don't have any reflections. Half a class. So you mean half a semester or something? If it's half a, it can't be half a class, half a lecture. It can't be half a lecture. That couldn't nearly cover the subject in a half a lecture. So yeah, it is. I'm just saying. So it's just a subtle difference, but I misunderstood because of the way they kept talking about layers. But the layers really, the layers. It's a distinctly different thing. A layer that has separation and a layer with no separation. Completely different animal. Because you didn't even think like an oil layer makes it kind of complicated. Because you think of layers that would like be impossible for the oil not to have contact with the glass. And that sort of makes sense to me. And it sort of is revealed in a sense that if you put oil between two pieces of glass, you don't see any extra or less reflection on the surface of the glass. So I haven't noticed any change in it. So it really depends on having a substance that is capable of creating that next layer. And liquids aren't very good at doing that. I mean, it's hard to have dirt between a layer of oil and a layer of glass. The dirt isn't going to stop the oil from making contact with the glass, or the water for that matter. So you still get refraction, but you don't get any reflection. Yeah, well, it's not just that it has to have thickness. Like I said, I can make water really thick, and that's not going to change the surface to glass relationship. So thickness is important, but it's still the connectedness and whether there's going to be a tendency, because they're physically in contact, the atoms will just transmit the light so easily because it's atom to atom. But if they're not atom to atom, then you have the problem of jumping the non-stuff surface. So if I could make glass, water, air, glass, you see what I'm saying? I mean, I obviously can't do that. But if I could do that, then you'd see my point, that the water to glass layer would behave very different than the water to air to glass layer. Yeah, it just has to do with whether there's atoms contacting atoms. And if there's no atoms contacting atoms, then you have reflection. If there's atoms contacting atoms, you have less chance of reflection. So it's the density of atoms that are contacting the other atoms of the other material. So if two materials are in contact, it's about whether or not the atoms are actually in contact with each other. And if they're not in contact, you have the possibility of reflection. If they are in contact, you eliminate the possibility of reflection. I won't say eliminate. That's probably too harsh. but you reduce reflection dramatically or something like that. Anyway, it is. I'm just saying it is a complex subject, so it really can hurt your brain trying to figure it out. Yeah. Anyway, let's see. Any other subjects? But yeah, I really would be good if I can get somebody with a little bit of exposure to attempt to make fun of me. I would appreciate that. Please, please, please troll me. High view people. Yeah. Try to humiliate me, please. Please try to embarrass me. Please try. I have to beg for it. Yeah, I appreciate it. Because, this show will be a lot better when there's more interaction. Talking physics makes a lot more sense when it's more than me talking. So anyway, let's see. Is that enough? Probably is. There are things I have to do. Don't want to do them. Just in so many bad habits lately. There was something I thought of. Let's see, what was it? Like a real obvious experiment to do. Well, I thought of a less obvious one, is the one we've talked about before, about the idea of putting an electric charge on the razor blades. So insulating two razor blades, putting an electric charge on them, and then doing the two-slit experiment to see as you dial up the charge whether you change the pattern at all. That really would be interesting to know for sure. So I just haven't seen it done. I frankly haven't even seen it done with magnets, but I don't think magnets are going to change anything much. But it is funny how I haven't seen it done. And there was some other experiment that was really simple I wanted to do. Oh yeah, this was kind of really interesting. So anyway, you can get, I buy some stuff at Harbor Freight now and then. And, they have really crap. It's crap, but it's cheap crap. So anyway, but they give away free things. So you can get a free multimeter sometimes. So I've got a bunch of them, like 5. And they're really crappy. Okay, so it's a really crappy multimeter. And so I put it on DC first, voltage, and thought, well, let's see if I can pick up any microwaves from my microwave oven, leaking. And I couldn't pick up anything. So then I did put it on AC, and the lowest whatever micro ampere kind of setting. And just with the probes, right? So I just grounded the black probe by holding it in my fingers. And then I just went around the door with the hot probe. And I got lots of indication of leakage. I got a voltage. So if you can do it with a shitty multimeter, I should be able to get maybe a really good multimeter. And I should be able to make a little antenna. And I should be able to make a little, a cheap version of a high frequency source and make a 2-slit thing and be able to prove my point that the energy's still there, that there is no interference. There's just jamming the radio signal, because it did pick up the microwaves leaking out of the door. I mean, not that my microwave couldn't be leaking a lot, but you sort of draw the conclusion that, well, it can't be that bad a leak, right? Or people be getting killed. So it is picking up a little bit of microwaves. So And, you know, it's close. Like I had the probe right up to the door, or the seam in the door. But the fact that it picked it up is a good sign that it's a doable experiment. So, yeah, so the guy who was working on it, like I said, Steve Bro, had some, like I said, he's hurt himself, hernia thing. It's, you know, who knows? So I don't know exactly what his status is, but he wasn't in very good shape. So he hasn't been able to finish what he started. But yeah, doesn't have to be done tomorrow anyway. But anyway, I was thinking about it, that maybe maybe there's a simple way to do the experiment that I can do on the cheap. So yeah, I just thought that was really interesting. I have to make some other radio sources and see how much I can pick up on just on a probe. Well, then I can make some antennas too. I can always make some better antennas to put on the probe and see what I can collect. And also, you know, if I insulate the probe wires, I should be able to get even more of a above the noise kind of reading. So, you know, something I have to work on. Lots of stuff. So, 32nd morning. Anybody has any questions or something they wish me to respond to? I was going to play the Ken Wheeler video. Actually, you know, the second half of that number 4 video on magnetism, he starts going into Fibonacci numbers. You know, it shows his swirly, whirly magnet drawings. Just complete horseshit. I mean, it was so much. I wish I almost played the second half, because it's so much worse than that first half I played. And the jargon, just, you know, counter space, blah, 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 bullshit. Okay, then. So we're done. All right. So till the next time and such. And thanks for the participation, questions, comments, whatever. Thank you. And till the next time and such. So forth and whatnot. I guess I'll try to contact Wham Pow guy. I mean, that other guy, that Boom Electro guy, is also a good guy to have debunk me, because he's funny. I like him. But he's a little samey too. It's kind of a gimmick, right? Like every time he does one of the experiments, he blows up capacitors on purpose just so he can go, you know, just so he can do this stick of, oh, look, I made a mistake. Yeah, no, you really didn't. Did it on purpose, you know, for the show. Just, you know, that becomes obvious after the 50th or 60th time you've seen him do it. It becomes kind of obvious that he's blowing up shit on purpose. But anyway. So till the next time and such.